This video is brought to you by mywayteaching.com.
In this part, let us see one more simple example. A charged metallic sphere A is suspended by a nylon thread. Another charged metallic sphere B, held by an insulating handle, is brought close to A, that is sphere A, such that the distance between their centers is 10 centimeter. You can see in the coming figure. The resulting repulsion of A is noted, for example, by shining a beam of light and measuring the deflection of its shadow on a screen. Spheres A and B are touched by uncharged spheres C and D, respectively. C and D are then removed and B is brought closer to A to a distance of 5 cm between their centers. So what is the expected repulsion of A on the basis of Coulomb's law? Spheres A and C and spheres B and D have identical sizes. Ignore the sizes of A and B in comparison to the separation between their centers, which means we can consider them as point charges. So here they have described the whole scenario in terms of figures. Now we should find the solution for this problem. So let us find the solution. So let the original charge on sphere A, we consider it as Q. Okay, the charge on sphere A. And the charge on sphere B, we'll consider it as Q dash. At a distance r between their centers, the magnitude of electrostatic force is given by F is equal to 1 by 4 pi epsilon naught Q dash by r square. So neglecting the sizes of spheres A and B in comparison to the distance, when an identical but uncharged sphere C touches A, then what happens, the charges will redistribute on A and C. And by symmetry, each sphere carries a charge of Q by 2. Similarly, when D touches B, again the redistribution of charges takes place and each will be having a charge of Q dash by 2. Now if the separation between A and B is half, then the magnitude of the electrostatic force on each, now it will become F is equal to 1 by 4 pi epsilon, since the charge will be half on each of that, and even, isn't it, which is equal to the same thing, 1 by 4 pi epsilon Q dash by r square. Thus the electrostatic force on A due to B remains unaltered. In this part, let us study forces between multiple charge. So we all studied about Coulomb's law. In that Coulomb's law, it gives the mutual electric force between two point charges, isn't it? Then, how to calculate the force on a charge where there are not one but several charges around? Consider this is charge Q1 and surrounding this there are multiple charges, not only two charges. So in that case, how to calculate the force on this charge Q1? Yes, there is a solution. Consider a system of n stationary charges, okay, from Q1 to Qn. Coulomb's law is not enough to answer this question, isn't it? And you can add these forces according to the parallelogram law of addition. See, force on any charge due to a number of other charges is nothing but the vector sum of all the forces on that charge due to the other charges taken one at a time. It is just the vector summation. The individual forces are unaffected due to the presence of other charges. This one we call it as principle of superposition. In order to understand this concept, you just consider a system with only three charges, Q1, Q2 and Q3. Okay. As you can see in this figure, the system with three charges, Q2 here, Q3 here and Q1 here. And here the force on one charge, say the force on Q1, due to the two other charges, that is due to Q2 and Q3, can be obtained by performing a vector addition of the forces due to each one of these charges, isn't it? Yes. Thus, if the force on Q1 due to Q2, the force on Q1 due to Q2 is denoted by F12. So that F12, we'll write it in terms of equation. So we can write the force on Q1 due to Q2 as F12 by Coulomb's law, that is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12 square and a unit vector, isn't it? In a similar way, the force on Q1 due to Q3, that also we can write, that is represented by F13. That is also 1 by 4 pi epsilon naught Q1 Q3 R13 square and a unit vector R13. Okay. This is it. Coulomb force on Q1 due to Q3 even though the other charge Q2 is present. So we can now calculate the total force F1 on Q1 due to two charges Q2 and Q3. So that will be equal to the vector summation 1 by 4 pi epsilon naught Q1 Q2 by R12 square plus 1 by 4 pi epsilon naught Q1 Q3 R13 square. This is the force on charge Q1 due to the other two charges Q2 and Q3 in a system. So this can be generalized for a system of n charges. See, the principle of superposition says that in a system of charges, that is from Q1 to Qn, you can take force on Q1 due to Q2 is same as given by Coulomb's law. Means it is unaffected by the other charges which are present in the system, as we saw in this particular case of three charges. So the total force F1 on charge Q1 due to all the other charges is given by the vector sum of the forces F12, F13 up to F1n. This is the total summation of charges, isn't it? Yes. So we can write the force F1 due to n charges present in the system in general, that is 1 by 4 pi epsilon naught Q1 Q2 by R square 1 2 Q1 Q3 and it goes till Q1 Qn. Okay, this is the total force. We can also write it in terms of sigma that is 1 by 4 pi epsilon naught sigma Q1 Qi R1I square R1I cap. This is the vector sum that is obtained as usual by the parallelogram law of addition of vectors. Now let us see a simple example here. Consider three charges Q1, Q2, Q3, each equal to Q at the vertices of an equilateral triangle of side 1. What is the force on charge Q with same sign as Q, which is placed at the centroid of the triangle? So here they have placed the charge Q, which is equal to Q. So now we should find the force on this charge which is placed at the centroid due to other charges Q1, Q2 and Q3 which are placed at the vertices of the triangle. See, in this given equilateral triangle ABC of side L, here the side they have given it as L, not 1. And if we draw perpendicular AD to the side BC, this is a perpendicular which is drawn AD to this side BC. So in that case, we can write AD is equal to AC cos 30, isn't it? So AC, how much? It is L, and cos 30 is 3 by 2. So it is 3 by 2 L. We know this. And the distance AO, A and this O of the centroid is given by 2 by 3 of AD. And we already know the value of AD. So if you substitute okay, this is 2 by 3 of AD. So by symmetry we can write AO is equal to BO is equal to CO, isn't it? Now let us find the force. See here, cos 30 is root 3 by 2. So AD is equal to AC cos 30. And cos 30 is root 3 by 2 and AC is L. And AO is given by 2 by 3 of AD. And we know the value of AD, that is root 3 by 2 into L. So which is given by 1 by root 3 into L. Okay. Now let us consider the forces. So the force on charge Q, which is at the centroid, that is force F1 on Q due to charge Q at A. That force is given by 3 by 4 pi epsilon naught Q by Q L square. And now this is along AO. And the force F2 on charge Q due to charge Q at point B, that is also given by 3 by 4 pi epsilon naught Q by L square. This is along DO. Now force F3 is given by, yes. So the resultant force of this F2 as well as F3 is given by same 3 according to parallelogram law. So now we can write the total force as zero, where r cap is the unit vector along OA. So it is clear also by symmetry that the three forces will sum to 0 at the centroid. Suppose the resultant force was non-zero but in some direction, consider what would have happened if the system was rotated through 60 degree about O.